inversion techniques. So before going to that, what are the procedure or what are the steps we have to follow to solve ODE? Just we'll see now. The first thing or first step, any ODE, any ordinary differential equation is given to you. It may be a second order, third order, or any order of the ODE is given to you. First step, you have to apply a Laplace transform on both sides of the equations. There will be a right hand side and left hand side will be there. You have to apply a Laplace transform on both sides. The second step, apply the given condition. In the problem, there will be a condition will be given like x of 0, x dash, x double dash of 0. What is the condition it's given? That condition also you have to apply it. Then step 3, obtain the Laplace form of the given ordinary differential equation. What is the Laplace? It will be in differential form. You have to obtain the Laplace form of the differential equation. Now, fourth step, you can solve by Laplace inversion by partial fraction method. Okay. So this part is very important. If you go to the fourth part, fourth step, how to solve by Laplace inversion by partial fraction method. Okay. So by solving this method, there will be a three category of problem you will see. Okay, what are the three category? One is the roots are different, the roots are same, the roots are imaginary. Okay, so what are the three different method? Roots are different, roots are same, and roots are imaginary. I think whatever the problem of any order of ODE is given to you, it will be coming under any one of these three category. Okay, let's see one by one how we are solving the ODE by using these techniques. Okay, now take a problem of solve d cube x by dt cube plus 2d squared x by dt squared minus dx by dt minus 2x equal to 4 plus e power 2t. The given condition x of 0 equal to 1, x dash of 0 equal to 0, x double dash of 0 equal to minus 1. So this is the problem statement given to you. You know this is the third order ordinary differential equation. We are going to solve by Laplace techniques. Okay. So the first step, apply a Laplace on both sides. Here left hand side and right hand side is there. Take the Laplace transform on both sides. If you are taking Laplace transform, so you know this is the cubic third order derivative. This is second order derivative. This is first order. This is a simple function. If you are going for third order derivative, what is the formula? S cube x of s minus s squared. X of 0 will come here. Here x of 0 will come. Then minus s into x dash of 0. X dash of 0 is 0 already. So that's why I am not given here. Then finally s cube x of s minus s squared x of 0 minus s into x of x dash of 0, then minus x double dash of 0. So x double dash of 0 is minus 1. Already one minus 1 is there. So plus 1 you will get. So this is the Laplace form of the d cube x by dt cube. Now, what is the Laplace form of the second term? The second term, take 2 commonly. This is the second order derivative. If you go to the second order derivative, s squared x of s minus s into x of 0. X of 0 is already 1 here. So, only s will come. Then minus, come to the first order derivative, s into x of s minus x of 0. X of 0 is 1 here. So, I have given directly the 1. Then minus 2 into x, if the function x, the Laplace of that function is x of s. So this is the Laplace form on left hand side. Now come to the right hand side. What is the Laplace of 4? 4 by s. We know already what is the Laplace of 1? 1 by s. So what is the Laplace of 4? 4 by s. Laplace of e power 2t is 1 upon s minus 2. So now the first step, we have taken Laplace on both sides, left hand side as well as the right hand side. Now after substituting the given condition, we have substituted all the given condition. What is x of 0, x dash and x double dash of 0. Okay, so now finally you will get the take x of s commonly, then take LCM on the right hand side. You will get the final Laplace form of the given ODE. This is the final Laplace form of the given ODE, that is x of s equal to something will be in the numerator and something will be the denominator. Okay, so this is the Laplace form of the given ordinary differential equation. Now the important step, we are going to solve this by using a inverse partial fraction method. So what is it? Now before going to that, I said there are three categories there. Roots are different, roots are imaginary, roots are same. So that we need to check now. Okay. For checking that, first thing, look at the denominator. So in the denominator, what is the characteristics of the roots you should check. Okay. Here s equal to 0 is one root, s equal to 2 is another root. This is the cubic equation. You know how to solve the cubic equation, how to find the roots of the cubic equation. This is the method. You take the coefficient of this cubic equation 1, 2, minus 1 and minus 2. If all the coefficient or any one of the coefficients is negative, you can start with the number 1. Okay, the remainder coming as 0, then 1 is one of the root. Then check the next level. In the next level, all the coefficients are positive, so you can try with the minus 1. If you are getting a remainder as 0, so minus 1 also one of the root. The next step, I tried with the minus, all the coefficients are positive. I tried with the minus 1, but I am not getting the remainder as 0. So I have gone to the minus 2. So if I am trying with minus 2, I got the remainder as 0. So minus 2 is also one of the root. So this is the way you are finding the roots of the cubic equation. Now 1, minus 2 are the roots of the equation. Now what are the roots behavior in the denominator? S equal to 0 is one root, 2, minus 1, 1 and minus 2. Look at the characteristics of the roots. All the roots are different here. Okay, none of the roots are same. All 5 roots are different here. So this is the one category of the problem. If you are finding all the roots are different, what is the rule number 1? So all the roots are different. So how many roots are there? That many constant you can introduce in the numerator. Here 5 roots we have. So we have introduced the 5 different constant A, B, C, D, E. Okay. Now we have obtained the form like that. Now in this form, take a LCM and you will get the form like it. Now look at the equation. The equation 1 and 3, the denominator are same. So you can equate the numerator. So in the numerator, just equate it. Now if you are applying a different value for s, you can eliminate the or you can determine the constant value. Okay. So now for example, if you are substituting s equals 0, you will get the value for a. If you are substituting s equal to 2, you will get the b value. If you are substituting s equal to 1, you will get the value of C, then like D and E, all the constant you have to eliminate and you have to determine it. So the constant value you have to substitute in the equation number 2, then you have to take the Laplace inverse of this one. Okay. So you know the what is the Laplace of inverse one? All the constant you can take it outside. What is the Laplace inverse of 1 by s is 1. 1 by s minus 2 is e power 2t. 1 by s minus 1 is e power t. 1 upon s plus 2 is e power minus 2t. 1 upon s plus 1 is e power minus tt. Okay. So this is the final answer for the given ODE. This is the final answer. We have solved the ODE by using Laplace techniques. Okay. Actually, you should think what is the use of this solving techniques. Okay. For example, this final answer will give the relationship between the time with some output variable. Okay. What is our ultimate aim in the control system? We wanted to maintain variable as constant even though the disturbance occur. Okay. You want to predict or you wanted to know the output condition at with different time. Okay, so here if you are substituting different value of t, you can come to know the output value. Okay, so the final equation will give you the relationship between the output variable with respect to the time. So that is the ultimate use of Laplace techniques in the control system. So this is one of the problem method. The roots are different. So now we'll go to the second problem. Take a problem. Again, this is the third order ODE. Okay. So third order ordinary differential equation is given to you with the given condition x of 0, x dash of 0, x double dash of 0 is 0. All the cases 0 here. So as usual, the first step, take Laplace on both sides. So if you are applying a Laplace on both sides, take a first term is the third order derivative. You know the formula for third order derivative. Then 3 into, this is the second order derivative. We know the formula for second order derivative, plus 3 into, this is the first order derivative. We know the first order derivative formula, plus x of s equal to, in the right hand side we have 1. What is the Laplace of 1? 1 is 1 by s. Okay. So now we have expanded the equation by applying the Laplace transform on both sides. After that, apply a condition. Here the x of 0, x dash, x double dash, all the cases are 0. So just substitute, you will get the form like that. Now you take x of s commonly, then you will find the Laplace form of the given ODE. So this is the Laplace form of the given ODE we obtained. So now we have to go for the solving of this Laplace form by partial inversion techniques. How to solve? The thing is now, look at the denominator. Before going to solve the problem, we need to analyze the characteristics or roots behavior. Okay. Here s equal to 0 is one root. Then look at here s plus 1 whole cube. Here s equal to minus 1, minus 1, minus 1. All three roots are same. Here what are the roots? 4 roots we have. S equal to 0 is one root. Then minus 1, minus 1, minus 1. All three remaining roots are same. So in the previous problem, the roots are different. So we have introduced the 5 different constants. But here the 3 roots are same and one is different. So what is the rule? Now we'll see. Okay. So if the roots are same, what is the rule number 2? You have to introduce the constant, then reduce the power in the denominator. How? Just listen here. So how many roots are there? 4 roots. We have introduced the 4 constant a, b, c, d. Then for s equals 0, we have introduced one constant. Then if the 3 roots are same, introduce the 3 constant b, c, d, reduce the power in the denominator. See in the denominator s plus 1 whole cube, s plus 1 squared, s plus 1. So we have reduced the power in the denominator, we have introduced the constant in the numerator. This is the rule number 2. So after that, as usual procedure, take LCM, then look at the equation, both equation, the denominators are same, so you can equate the numerator. So in that, if you are equating the numerator, substitute different value for s. For example, if you are substituting s equals 0, you can find the answer for a. But if the roots are same, one of the problem, you cannot go with the substitution, so you have to expand the whole equation. So after expanding the equation, you can compare the coefficient of SQ on both sides. You can get the answer for D. Then if you can compare the coefficient of S squared on both sides, you can get the answer for C. Then substitute all the values in the equation. Then take Laplace inverse of that equation. Okay. So here, if you are going for Laplace inverse techniques here, this is some problem is there in this problem. We know already what is the Laplace inverse of 1 by s is 1. Now here, what is the Laplace inverse of 1 upon s plus 1 whole cube? Anywhere, if you are going for the Laplace inverse techniques, it should be in the common format. Okay. We have never seen the format s plus 1 whole cube. Okay. Now what we have to do here? Here the s is replaced by s plus 1. So you can take, it is e power minus t outside. Then only 1 upon s cube it is there. Here second term also you take, here s is replaced by s plus 1. Take that is e power minus t, then Laplace inverse of 1 upon s square. Then here s is replaced by s plus 1. Take e power minus t, then Laplace inverse of 1 by s. Okay. So now find the Laplace inverse of remaining thing. This is as usual case only. But here what is the Laplace inverse of 1 by